Imagine a tiny roulette wheel made of pure light. You tap two wires with your finger and suddenly the LEDs race faster than your eye can follow. Then slowly they begin to decelerate one by one until only a single LED remains lit. Hey guys, in this video I'm going to show you how to build this hypnotic touch-activated light spinning circuit using just a 555 timer and a few simple components. No casino chips required. Stay tuned to the second part of this video where I'll explain how this circuit works. I've packed my favorite 555 timer projects into a free ebook. Yep, totally free. Don't miss it. Click the link in the description to get yours. Here are all the components you need to set up this circuit. 38 jumper wires, two 4.7 mega ohm resistors, one 2 mega ohm resistor, one 10 kilo ohm resistor, one 470 ohm resistor, 10 red LEDs, a 9-volt battery, a 9-volt battery buckle connector, a 1 microfarad capacitor, one BC557 transistor, one 100 nanofarad ceramic capacitor, one CD4017 decade counter, one 555 timer IC, a breadboard to connect everything together. The 555 timer IC comes with 8 pins. There is a notch or a dot on the chip's body. Starting from the top left is pin 1, which is ground or the ground supply. Pin 2 is trigger. It is used to start the timing interval in both monostable and astable modes. Pin 3 is output. It delivers the result of the timer's operation based on its mode, either monostable, astable, or bistable. Pin 4 is reset. It is used to reset the 555 timer's internal flip-flop. Pin 5 is control. It allows you to control the threshold voltage levels that the internal comparators use to set and reset the flip-flop. Pin 6 is threshold. It monitors the voltage of the capacitor connected to the circuit. Pin 7 is discharge. It controls the charge and discharge cycle of the timing capacitor. Pin 8 is VCC. It is responsible for supplying the power to the IC. Let's set up the circuit step by step. Start by placing the 555 timer IC onto the breadboard. Remember, the pins are numbered counterclockwise, starting from the top left. Refer to the later circuit diagram if you have questions about the circuit connections. Insert the 555 timer in the middle of the breadboard. A jumper wire connects pin 1 or ground to the negative rail. A jumper wire connects pin 8 or VCC to the positive rail. Use a jumper wire to connect pin 2 or trigger to pin 6 or threshold. Use a jumper wire to connect pin 4 or reset to pin 8 or VCC. Insert a jumper wire into pin 6 or threshold and pin 7 or discharge. Insert a 100 nanofarad ceramic capacitor into pin 2 or trigger in the negative rail. Bend the ends of a 4.7 mega ohm resistor. Insert the 4.7 mega ohm resistor into pin 2 or trigger in the negative rail. Insert a BC557 transistor a few rows above the 555 timer. Insert a jumper wire in the same row as the collector of the transistor and the positive rail. Bend the ends of a 10 kilo ohm resistor. Insert the 10 kilo ohm resistor into pin 7 or discharge and the emitter of the transistor. Bend the ends of a 2 mega ohm resistor. Insert the 2 mega ohm resistor into the base of the transistor and the positive rail. Bend the ends of a 4.7 mega ohm resistor. Insert the 4.7 mega ohm resistor into the base of the transistor and a few rows above the transistor. Insert a 1 microfarad capacitor in the same row as the 4.7 mega ohm resistor and the positive rail. The anode is in the positive rail. Insert a jumper wire in the same row as the 4.7 mega ohm resistor. Insert a jumper wire on the other side of the central gap. Insert a jumper wire in the same row as the other jumper wire and the negative rail. Insert a CD 4017 decade counter in the middle of the breadboard. Insert it a few rows below the 555 timer. Insert a jumper wire into pin 3 of the 555 and pin 14 of the 4017. Insert a jumper wire into pin 8 and the negative rail. Insert a jumper wire into pin 16 and the positive rail. Insert a jumper wire into pin 15 and the negative rail. Insert a jumper wire into pin 13 and the negative rail. Insert a jumper wire into pin 3 in a row below the 4017. Insert a red LED into the same row as the jumper wire and a row below it. The anode is in the same row as the jumper wire. Insert a jumper wire in the same row as the cathode of the LED and the lower half of the breadboard. Insert a jumper wire into pin 2 and 4 rows below the first LED. Insert a red LED into the same row as the jumper wire and a row below it. The anode is in the same row as the jumper wire. Place the LED in the center of the right side of the breadboard. Insert a jumper wire in the same row as the cathode of the LED and the same row as the other jumper wire. Insert a jumper wire into pin 4 and 4 rows below the second LED. Insert a red LED into the same row as the jumper wire and a row below it. The anode is in the same row as the jumper wire. Place the LED in the last column on the right side of the breadboard. Insert a jumper wire in the same row as the cathode of the LED and the same row as the other jumper wire. Insert a jumper wire into pin 7 and 4 rows below the third LED. Insert a red LED into the same row as the jumper wire and a row below it. The anode is in the same row as the jumper wire. Place the LED in the center of the right side of the breadboard. Because all these jumper wires need to be connected, add another jumper wire 3 rows below them to link the rows together. Insert a jumper wire to connect the gap. Insert a jumper wire similar to the right side of the breadboard. Bend the ends of a 470 ohm resistor. Insert the 470 ohm resistor in the same row as the jumper wire and the negative rail. Insert a jumper wire in the same row as the cathode of the LED and the newly connected row. Insert a jumper wire into pin 10 and 4 rows below the fourth LED. Insert a red LED into the same row as the jumper wire and a row below it. Place the LED in the first column of the right side of the breadboard. Insert a jumper wire in the same row as the cathode of the LED and the newly connected row. This time we're connecting the left side of the breadboard. Insert a jumper wire from pin 1 to the lower half of the breadboard. Connect a jumper wire from pin 5 to the lower section of the breadboard, ensuring it's placed in the same row as the previous wire. Insert a jumper wire from pin 6 to the lower half of the breadboard. Insert a jumper wire from pin 9 to the lower half of the breadboard. Insert a jumper wire from pin 11 to the lower half of the breadboard. Use a jumper wire to connect the negative rails together. Attach the buckle connector to the 9-volt battery. It's time to connect the power supply. Connect the positive lead of the battery holder to the positive rail. Connect the negative lead of the battery holder to the negative rail. When I touch the two wires, the LEDs light up one by one in a circular pattern. Once I lift my finger, the rotating LED gradually slows down and comes to a stop. We have successfully completed the circuit. Let's dive into the circuit and break it down step by step. This little roulette-style rotating LEDs circuit breaks down into 3 cooperating subsystems: an impulse and decay network, and a stable 555 timer, and a CD4017 decade counter that drives a ring of 10 LEDs. Power arrives from a 9-volt battery and feeds every section. To the left of the schematic, you see a 1 microfarad capacitor sitting between the supply rail and a pair of touch wires. In the idle state, the capacitor is fully charged to the battery voltage, so the PNP transistor above the 10 kilo ohm resistor is off. The moment you bridge the touch wires with a finger, your skin resistance pulls the transistor's base toward ground. That sudden base emitter voltage slams the PNP into saturation, effectively shorting the 10 kilo ohm resistor to the positive rail. Because that 10 kilo ohm is the charging path for the 555's timing capacitor, the oscillator inside the 555 rockets to its highest possible frequency, well into the kilohertz range, producing a rapid-fire stream of clock pulses. As soon as you let go, the 1 microfarad capacitor starts to recharge through the 2 mega-ohm resistor. That long resistor-capacitor time constant pulls the transistor gradually back toward cutoff. So the 10 kilo ohm fast path fades out, and the only remaining timing resistor is the 4.7 mega-ohm that had been tied to ground all along. The charging and discharging current through the 100 nanofarad capacitor at pins 2 and 6 therefore drops exponentially. The 555's square wave output begins in a blur, slows smoothly through dozens of cycles per second, and crawls to a halt somewhere below 1 Hz. The process feels exactly like a roulette wheel losing momentum under friction. Those pulses march straight into the clock pin of the 4017. The chip's Q0 through Q9 outputs step high one at a time for each rising edge they see. So at high speed, every LED on the ring seems lit continuously. As the frequency decays, the pattern resolves into a bright spot that races around the ring, then hops more and more slowly until one LED remains lit. All 10 LEDs share a single 470 ohm current limiting resistor back to ground, which is safe because only one output is high at any moment. The beauty of the design is that you get all that drama: instant acceleration, graceful slowdown, and a final random stop, without any microcontroller or motors. If you want a longer spin, you simply increase either the 1 microfarad capacitor or the 2 mega ohm resistor. You can also cascade another 4017 for 20 LEDs, or tweak small capacitors across the clock line to sharpen the final snap as the LEDs slow. I hope this video has shown you how to make rotating LEDs with 555 timer ICs. Want to dive deeper into 555 timer projects? Grab my free ebook packed with awesome circuits and ideas. Don't miss it. Click the link in the description to get yours. If you found this video helpful, give it a thumbs up, consider subscribing for more electronics tips and tutorials, and hit the bell icon to never miss an update. Thanks for watching, and I'll see you in the next video.